so that Riley and all the other sickies can do this.
Where is it going to be?
All right.
And how do you want to turn that work right now?
No. We'll handle all the work so far. Now, when we do, if we do go virtual, then I'll have it to where you can. If it's a short amount of time, I'll just tell you to hold your work until we get back, because having to take pictures of it and post online sucks.
I did that for all.
It's easy for Google Classroom. I don't know about.
Yeah.
I had to do it for
Well, for Canvas, it's not bad, except for unless you have to take JPEGs. You've got to just trust
Google
me.
Classroom, you look
Hold
at
on
my
to it.
attachment and you.
Yeah. All right. So binomial probabilities. Let's get going here. The binomial probability, and let me move to where you can see. I'm back here. You're up there. All right. If you can't see, might I recommend you move up or over so you can see.
Those are COVID exposed.
So are you.
This one
You're
is.
like in COVID Central there. All right. Binomial probability. Let's remember, what did the bins in binomial, what did the B stand for?
Two. Hang on.
Binary.
Binary.
Two possible outcomes.
Binary. Two possible outcomes, success or failure. Okay, this is important that you know how to do this, because if you have to do it by hand, and you did this in pre-cal, and I know for a fact you've all had pre-cal because I taught most of you. Binomial, remember when we did Pascal and we did binomial expansions, there was a way to find that coefficient that went in the front? We're going to be using that same idea with binomial probability. So you've got that NCR piece. That gives you part of that equation, okay? So binomial probability is, if we look at this, probability we get K successes. Notice it is defined as successes with the probability P of success and then 1 minus P of failure. And then finally we have N trials. Notice, remember, we had independent and a set number of trials. So for binomial, we have a set number of trials. Okay? So what we have to look at is, what is the formula? And this is where the binomial formula comes into play. Notice this right here says number of arrangements of K successes, because we ran into a problem with that, didn't we? When we had to do all our flipping coin thing, we had to do the factor tree so we could see all the different ends, which were all the different possibilities. Turns out that if you're doing a flipping coin problem or something like that, you don't have to do that tree. You can figure out how many combinations there would be using NCR function in your calculator. In other words, finding all the combinations. It's a combinatorial. All right? That is your NCR here. Now, they don't write it that way in statistics. In statistics, if you remember, we wrote this in pre-cal. If you remember, we wrote this in pre-cal. I know it's been a while. We wrote this as NR, didn't we? Now, we have just defined P of X equals X. This is going to be whatever we're looking for, which is probably the number of successes, right? The number of successes. So instead of NR, we're going to write this as NX times P to the X and 1 minus P to the N minus X. So let's break this down. This right here stands for the number of combinations. P is the probability of success, isn't it? And that's how many successes we're looking for. This is the number of successes. And then 1 minus P is what? Failures. This is the probability of failure. And guess what N minus X stands for? Think about it. It's the number of failures. If N is the total number of trials and X of them are successes, then how do you figure out how many failures you have? The rest of them have to be failures, don't they? So that's N minus X. So does everybody understand how this kind of goes together? Now, for you, luckily, if you don't have to do it by hand, then you've got Binomial Pdf and Binomial CDF that you don't have to use this formula for. You just put in P and X and N, and it pops out a number for you. But in the multiple choice section of the exam, it's going to write it out in this form right here. You've got to know how this form looks, because if you don't, you won't be able to figure it out, will you? All right. So how do we find the number of arrangements? Binomial coefficient. That's where Pascal comes into play, right? This binomial NR, the combinatorial, that's the number of combinations. Okay, you can use Pascal's triangle for the binomial coefficient, which is factorial. And every once in a while, you do see the factorial come out here, guys. Notice that that is x is n factorial over x factorial times n minus x factorial. That is the actual mathematical part of it, okay? Chances are you'll never have to do this. And remember, 0 factorial is 1.
No? Is there some, like, we're just long
Magic. Think about Pascal's triangle. What does every row of Pascal's triangle start with? There can never be 0 combinations, can there? If you're looking for something, the minimum number of combinations you can have is 1. And that's why there's 1s at the edges and never a 0 in Pascal's triangle. And remember, 0 factorial represents that first possibility. In other words, 0 failures or 0 successes, which would mean you have the opposite number of failures, right? You'd have n failures. 0 successes means n failures. So you can never have it completely go away. If you don't have successes, you have to have failures. That's why 0 factorial cannot be 0. It's one goes the other. What?
That's a good quote. We'll put
Yes.
it on this quote.
Cool. All right. So we can rewrite the binomial. And so we've rewritten this. We've got this. K is what we're looking for, right? So now, look what it says right here. Good news. Oh, we love those statements. Good news is your calculator can calculate binomial probabilities for you quickly and easily. Now, here's the thing you need to know about. If they are individual, you use PDF. If it is cumulative, you use CDF. C for cumulative. I always say P is for a particular value, right?
Good one.
So we use PDF for an individual K. So if I wanted to know, if I were flipping a coin and I wanted to know the probability of, after 5 flips, of one of them being heads, that would be a binomial PDF problem, right? I'm just looking for one. If I wanted to know the probability of getting one or more, that would be a CDF problem. Do you see the difference? Equal versus what? Between 0 and x, inclusive. Notice what it says here. Inclusive means it's always less than or equal to. So here's the problem with binomial CDF. What if I just want to know less than 4? In this world, less than 4 would be, you could approach it 2 different ways. 4 or less, and then we have to subtract out the possibility of 4. But if we do that, that means really it's 3 or less, isn't it? So you've got to think about what the problem is actually asking you. If it does not include, if it's not part of the inclusive, you can't just throw it into CDF and say this is the answer. All right, so let's take and look at a couple examples where we have to kind of do this the long way. I love Chewy. Star Wars cards were in a quarter of cereal boxes advertising the new upcoming Star Wars movie. 2 cereal boxes are purchased. So we got to go through and we've got to decide, before we can use binomial, we have to decide if it matches our criteria, don't we? Is this problem going to be a binomial?
Yes.
Is it binary?
Yes.
You either what?
Got a card or you don't?
Got a card or don't have a card? Yes. Card, no card. So let's define that. So C is,
Whoa.
C is we have a card. Ooh, I don't like that. or n is no card. So it is binary. Every time we get a card, is that independent of the other serial box? So whether one card has it, is not, one box has it is not dependent on whether another box has it. So it passes independent, doesn't it?
Yeah.
Do we have a set number, n?
Yeah, 2 boxes.
2 boxes. So our little n is 2. Okay? Do we have the same chance every time we get a box?
Yeah, 1/4.
Yes, 1/4. So our p, this is a chance of success, remember? Sometimes they give you failure and you have to find success. If they give me failure and I have to find success, what do? Subtract it from 1, right? So p is 1/4, which is 0.25. So it passes bins. So this is a binary scenario. And notice that's part of our thing today was, could we identify a binary setting and then find the probability? So now it says find the following probabilities. Ooh. Using your calculator function.
How we do that?
Now, we could do this, guys. Guess what? We could do this using a tree. You can tree diagram any of these if you like to. You don't have to use Binomial CDF and Binomial PDF, but if you like a factor tree, first box we can what? Card or?
No card.
No card. This is going to be 1/4, 3/4. Second box would be?
Card or no card.
Or?
Card or no card. Card or no card.
So this is still going to be 1/4 again,
And 1/4 again.
and 3/4. 1/4, 3/4. So 1/4 times 1/4, this is 1/16. This is going to be 3/16, 3/16, and 9/16. All right. So let's do this both ways so we can compare. Okay? So that way we know we're doing it right. I like to give you alternative methods to do things. So if you don't like it the one way, you can do it the other way if it makes sense to you. Probability that neither box has a card. Hi. Yes, I did. I watched all that stuff. I'm sorry. I just couldn't sign. Uh-huh. All right. Neither box has a card. It's going to be what?
Sign your death certificate.
Yes, that was my death certificate. How morbid. That would be this branch right here, wouldn't it? No card, no card?
Mm-hmm.
So what's the answer?
9/16.
9 out of 16. So let's do this the old-fashioned way, though. Is this a PDF or a CDF?
P.
This is a PDF. So instead, for this first guy, let's go down here. And let's do this as a binomial PDF. So where do we find PDF?
Second bars.
Second vars, right?
Go down. Roll out.
So second vars, we're going to go all the way or up. You know, if you go up, you can go the other direction.
Yeah, it goes all the way to. Oh, it goes
How many trials?
2.
binomial.
2 trials. What is the success value?
1/4.
1/4, 0.25. You can put it in as 1 divided by 4. 0.25. What is my x value, though? No.
2.
X value is how many successes if there are no cards?
0.
0. And then we hit. So put that down.
Wait, x values how many?
We're doing n is 2, p is 0.25, and x is 0. X is the number of successes we're looking for. No card means x is 0, doesn't it?
So we're looking for one.
Probability neither box has a card.
Oh, we're on the top.
Yeah, I'm just letting you figure out how to do this.
Yeah.
Okay, so hit paste and then hit enter, and what do you get?
0.5625.
0.5625, which if you take that answer, hit math, and go down to fraction,
Oh my gosh, I've been wanting to know how to do this for so
Thanks.
long.
and hit enter.
Yeah, I couldn't
Wow.
figure out how to do that forever.
And it tells you, doesn't it?
Yes,
9/16. So it checks out, doesn't it? So which one's easier?
I like the tree, honestly.
The tree's more satisfying.
Pick your poison.
I feel like I'm.
If you can't figure out the tree, however, or if the tree is going to be too big, then you've got a second tool, don't you? Okay. I don't care which one you use. They're both, there's 2 roads. There's more than one road to the right answer, isn't there?
Either way you get.
You go around one way, I go around the other. We both get to the same answer. That's right, I get paid either way. Probability that one box has a card. Be careful. Probability that one box has a card, I'm going to use red. Could be this.
Yeah.
Or,
Do you add them?
yes, you have to add them.
6/16.
So this is 6/16.
You just want to simplify it.
So you don't have to simplify.
You don't have to.
Never hit this before.
Well, I get my calculator and I get 3/8.
Wow.
That's
It's the
fine.
Same thing.
Yep. So now let's try it again. This time, binomial PDF. N equals 2 still, doesn't it? P is still equal to 0.25, only this time x equals what?
No.
1. So really quick, second vars, binomial PDF, just arrow down to one value instead,
I'm looking for x equals 1.
0.375, right? Which is
But your x is how many successes?
3/8.
Yeah, so on this
So
next
you're
one,
looking for how many zeros?
next one, we'll use
Because it's so x
Still
equals
equal.
2. X equals 2.
Both boxes have a card is just 2.
We're not looking, like if it said x is greater than equal to 1.
If it had asked you, what's the probability, here's the difference. If it asked you what would be the probability of getting one or fewer cards,
Oh, okay.
that would be less than or equal to, right? Or one or more cards.
CDF.
That would be greater than or equal to. Here's the problem. Look what it says up here. What if I asked you, here's a good question.
Okay.
What is the probability of getting one or more cards in 2 boxes?
So it'd be 1 or greater.
Yes, so this is the x is greater than or equal to 1.
1.
Here's the problem. Look right here. What does it say right here? It only does what? Less than or equal to, doesn't it? We can't do greater than or equal to on PDF, binomial CDF. It only ever does less than or equal to. So this is what I suggest you do.
Try.
No,
You don't just do it, subtract from 1.
I want you to think about it this way. Yes, that's exactly what you would do. But look, we've got 2 possibilities, don't we? So if we want greater than or equal to 1, here's 1. We want greater than or equal to 1. Binomial CDF will only do what? Less than or equal to 1. But the problem is that this is part of this, isn't it? So here's my big problem.
There's overlap.
Yeah, this is the way I suggest you think of it. Successes are 0, 1, or 2, aren't they? So if I want 1 or greater, don't ever look at it on a curve because you're tempted to. Look at it on your distribution. 1 or greater would be the same as 1 minus what? 0, wouldn't it? Do you see how this tells you that? Because the 1 is included in this, which means that if we do 1 or greater, then the only thing left for us to look at would be subtracting out the bottom part that we don't have. Okay? Yes? No?
Yeah.
Yeah. All right. All right, so 1 minus P of 0. Well, we know that, so we can write this in one of 2 ways. We can either write this as doing 1 minus binomial PDF of what? N equals 2, P is 0.25, and then 0, right? We know that, don't we? We could write it as 1 minus the probability of x equals 0. That's one way we could write it. I prefer this way, and so will the committee of graders. Write it as a probability statement. Didn't we already find that?
Yeah, 9/16.
So we do 1 minus 9/16. And you can do that on your calculator, can't you? What would that be?
I mean, just like, 14375 or
7/16?
Yeah. could just do 16 minus 9.
All right. How do we get 7/16 from the tree? This is 0. So that would be the rest of them, wouldn't it?
That's getting one or more.
This would be, yeah, greater than or equal to 1. That'd be 1 or more. So we can still get it off the factor tree.
Yeah.
So, all right, so is everybody good with this? How we do these types of problems? That's going to be the single biggest thing that you mess up on is when you have greater than or equal to, you'll forget that binomial PDF, CDF only does less than or equal to. Got it? Probability getting 2 would have been this one, wouldn't it?
Yes.
That length? Okay. Rewrite it. So here we go. What do you notice about Pascal's triangle? Y'all all know this, don't you? Well, there's Pascal's triangle for you.
I don't think I've ever
I hate Pascal. I hate
I'm
this
serious.
whole
I took freak out last year and I don't
Pascal's
think, I
triangle last
don't
year.
remember looking at this.
Well, my group did it.
It's
I had-
awful.
I had,
Single-handedly the worst thing we did last year.
you really
And it's not even close.
You really think?
I hated Pascal's triangle. Like so much.
You hated it worse than analytical trig?
Yes.
Wow.
Y'all did stuff I don't even
I did
talk
not
about.
get this.
Well, all you have to be able to get is how do I find it on my calculator? NCR, right? Or, okay. Says complete the binomial probability distribution below with your results from above and verify that it is a valid probability distribution. So what was the probability of getting 0?
9/16.
What was the probability of 1?
3/8.
No, it was 6 because you added them both up.
Now, why am I doing it this way? Because I need to make sure they all add up, don't I?
Oh, no.
And then what was the probability of getting 2?
The rest.
Whatever the rest of it.
1/16, if you look at it, right? Think of, so, cumulative probability. This is 9/16. 9 plus 6 is,
15.
and then 15 plus 1/16 is 16 over 16, which is
Uno.
1. And doesn't this prove that it is a valid distribution?
Yeah.
Adds up to 1.
The piggy Pablo, no.
Okay. Now this also helps you though when you're doing those types of problems if you're doing greater than or equal to, right? Okay, so use your calculator, verify we did that already, didn't we?
Yes.
Yes, we did.
Look at us.
And it says make a histogram of the binomial distribution. Do we really need to make the histogram?
I don't want to.
Let's just look at the histogram of the binomial distribution just because I want to show something to you. What do you notice?
It's a history.
0, 1, 2. And we got to go from 0 to 16/16, right? So this would be 8/16. What's the probability of getting 1 or 0? A little over that, right? The probability of getting 1 is 6 out of 16, which is like down here, isn't it?
Sure.
Probability of getting 1 is that. Yes, I know the bars should touch.
Jesus.
Sorry. Bars should touch.
I don't even know what I'm looking at right now.
What I want you to notice though is what is it not? It's not normal, is it?
No.
Very weird.
This is not a normal distribution.
It's degrade or.
Near gonna be normal. Doesn't that make sense though? That's,
He's right.
it just doesn't work that way. So let's look at exercise here. 60% of all computers sold by a large company retailer are laptops.
I picked that up.
So this is important. So 60% are laptops, 40% are desktop. The type of computer purchased by each of the next 12 customers will be recorded.
Why did they spell out 60% or put 40%?
I don't know.
That bothers me.
You're wasting time.
These people don't. These people.
Whatever we don't get through today, it will be recorded for you, and you will have to do on your own.
Okay.
So let's stay on task. What does this 12 customers recorded tell me?
It's a finite amount of.
Finite number. So already we have n equals 12. So let's define a random variable as the number of what?
Laptop.
Laptops. So x is number of laptops purchased. So does this make it binary? What would be success?
Laptop.
You bought a laptop. That means failure would be what?
Not a laptop.
Not a laptop, which would then, as a result, be a desktop, wouldn't it?
Yeah.
Okay. What's the probability that exactly 4 are laptops?
So P.
So let's write this out the long way, and then we'll use, yes, because you've got to be able to identify it on the multiple choice section, don't you? So P is what? We know N is 12, right?
Yeah.
P is what? What's the probability of success?
60% or 0.6.
That's purchasing all computers. We want to know success is a laptop.
Yeah, 60% of all computers are laptops.
Oh, yeah, desktop. Duh. 0.6. Thank you. Yes, my brain hurts now. All right. And what is X? Okay. So what is that? Is it equal, greater than, less than? What is it?
Equal.
Exactly 4 means it equals 4. So now let's take this part A. I'm going to take part A down here. And we're going to write it out in the long form of the problem. That means we're going to write it out this way. So what is my formula? N what? X. So this is 12 over what? 4.
That's 3.
Success is what?
0.6.
0.6, but it should be 0.6 to what power? The 4th, because we did 4 successful laptop purchases. If 0.6 is success, then what is failure? 0.4, which is 1 minus 0.6, isn't it? So I'm going to write this as 0.4, but please remember that this comes from 1 minus 0.6. Gave me my 0.4. And what number goes up with it?
8.
Why 8?
Because it's N minus X.
Yeah, it's N minus X, your failures, right? If you had 4 successes out of 12 trials, 12 minus 4 is 8. Okay. That's how you would see it on the exam in the multiple choice section. That's how it would write it. Now, how are we going to actually solve it? Calculator, for sure. Binomial PDF this time, isn't it?
Indeed.
And we're going to write N equals 12, P equals 0.6, and X equals 4. And you're going to tell me what you get.
0.042.
Yes.
0.42.
If you didn't want to do that, you could just work this straight out of your calculator. Do it using this form. You know that. You could plug this into your calculator, couldn't you? NCR. This is your NCR, isn't it? And that's under math probability in your calculator. So if you don't want to use Binomial PDF, you can just do it the long way. I got 0.042. Did you?
Yes.
Okay. Part B. All 12 of the customers purchase a computer. What's the probability that less than 3 are laptops?
What?
So if you have to write this out the long way, and we're going to write this out the long way. Less than 3 means what? You could have purchased 0, or you could have purchased 1, or you could have purchased 2. Remember, the long way is just individual PDFs. So how would we know that? What are the possibilities out of 12? You could have done 0, 1, 2, 3, 4, 5, 6, and so on, couldn't you?
Yeah.
Less than 3 would have been what?
Just 2, 1 and
That, wouldn't it? That tells you, this right here tells you this. 12, 0, 6, 0.412 plus 12, 1, 0.61, 0.411 plus 12, 2, 0.62, 0.4, 10. That's the long way. See why binomial CDF is such a treasure? Because do you want to have to do that individually?
No.
No, that kind of sucks, doesn't it? Yeah.
Just a lot.
So if we wanted to do 3 or more, here's the cool thing though. This is a lot because this technically this distribution goes all the way out to x equals 12, doesn't it? So if we want to do 3 or more and we had to do it individually, we would have to do 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12. Or we could do 1 minus, in parentheses, 0 plus 1 plus 2, right? 3 or more could simply be 1 minus what's left in the distribution, couldn't it? Does everybody get that? So if we were actually going to do, because I'll show you how to write it to see 3 or more. So here we go. Let's just do this one though. Is this a good binomial CDF question? Yeah. CDF does what? Less than or equal to. So this is perfect. So we can do binomial CDF n equals 12, p equals 0.6, and x equals what this time? 2. The highest number right here, right? 2. Is this going to be a very big number? Probably not, right?
0.003. Yes. What he said.
Yeah. 0.003. So now let's throw one more in and ask ourselves if we wanted to do, what's the probability of x being greater than or equal to 5? If somebody purchasing 5 or more laptops, or 5 or more laptops being purchased out of 12 people. 5 or more. How would we approach this using our distribution table? 5 or more would be this, wouldn't it? On up?
Yeah.
So instead, we would approach this as what?
Find 4 or less.
Yes,
And
1
subtract from 1.
minus the probability of. Do you see how this structure of writing out the actual probability distribution table can help you successfully work these problems without screwing them up? Always think about what the probability distribution table would look like for these types where it's greater than or less than, right? Especially greater than. So this guy we could use, once we've got it in terms of less than, then we can do 1 minus binomial CDF, n equals 12, p is 0.6, and x equals what? 4. And you can do the 1 minus and then put the rest of it in. Or you can just do it separately and then do 1 minus answer.
How do you do 1 minus answer?
Did you find binomial CDF? Do 1 minus and then do second, and right above the negative, it says answer.
0.943.
Okay. Did everybody else get 0.943?
Yeah.
So do we get how to do this now? You can see why I wanted to get through this together. All right. So let's look at,
You need the homework to be this and only this. Yes, we do.
it is only going to be binomial stuff.
Let's go. Is it going to be mine?
We'll save geometric for the next time. So, exercise. To introduce her class to binomial distributions, Mrs. Bates creates a quiz game. There are 20 questions with multiple choice options A through E. Here's the catch. The students must decide before the question appears what your answer is going to be. What is your answer going to be?
B, C.
Exactly. Mrs. Bates created the answer key with a random number generator.
She's evil.
Casey's one of the students in the class. Let X be the number of Casey's correct guesses. So first things first is let's decide whether or not it's binomial. So does it pass bins?
Yes.
Okay.
Right or wrong?
Yeah.
Right or wrong?
Correct. Let's use the phrasing they used. Correct or incorrect, so yes. Since she used a random number generator for each answer in the answer key, are they independent? Yeah, they were randomly generated. They are independent. No question depends on any other question. Each question independent of other questions. Okay? Let me make that bigger so you can see it in the back. All right, N.
20 questions.
20 questions. So that works. And P, or S, which is P, right? The bins is S. What is the probability of getting a correct answer? 20%, which is 1 out of 5. Why 1 out of 5?
Because she's randomly generating the correct
Because
answer.
A through E is how many options?
5.
5 options. So you can, 1 out of the 5 is correct, right? So they're not just going to go ahead and hand you P, are they? Sometimes you're going to have to figure out what P is. Is everybody good with that? Does everybody understand where the 1/5 came from? We would write it as 1/5. We could write that as 0.20 because that is 20%. So now it says find P of x equals 7 and explain what that means.
Okay.
So let's start with the x equals 7. What does x equals 7 mean?
Correct answers.
That's the probability of
7 correct answers.
context. Casey getting 7 exactly 7 correct answers. Why would I want to use that word exactly?
Because you don't want to have the less than or whatever.
Exactly. I don't want any questions. I want it says 7 questions, only 7, not greater than, not less than. So the explanation would be the probability Casey guesses exactly 7 questions correctly is, and then we'll figure it out. Now we have to actually find that. So what are we going to use?
Binomial
Pdf, where n is what? 20. P is 0.2. And x is 7.
Or sorry, 0.055.
0.055. How are we doing back there, ladies? Are we okay? I'm not going too fast? Okay. To get a passing score on the quiz, a student must guess correctly at least 12 times.
I hate this.
Would you be surprised if Patty earned a passing score? At least 12 times. So let's write this as a probability statement. The probability of x is what? Greater than or equal to 12. That should mean, can we do greater than or equal to 12? So we need to rewrite this as 1 minus what?
Probability less than or equal to 11.
Less than 11. Or equal to 11, yes, because it does less than or equal to, right? All right, because there is no in between here, is there? This is a discrete distribution, isn't it?
You wouldn't be able to do it with the other one, can you?
Which other one?
The not discrete, but whatever the other word is.
Continuous? No.
Continuous. Like you can't do it because you can do it.
Yeah. The nature of binomial says that it has to be a set number, right?
So, I mean,
So you have to have a set demarcation.
would they try to do that?
No.
No.
No, they're not going to try to trip you up. Yeah. No. Now, how will you see this on the multiple choice section? This is how you'll see the answer possibilities in the multiple choice section. 1 minus, let's see, That would be one of your choices on the multiple choice section. And they might switch around. They might make this a 12 to see if you got it. They might make this a 12. They might switch these two around. They might switch these around. You see the possibilities? But if you can write it this way, then you can identify that it's got to be 1 minus something, right? They might put just this as possibility with a 12 there. See what I'm saying? There's lots of ways they can trip you up trying to do this. We don't want them to. So now we are going to then, if it's not multiple choice, if it's part of a problem solving FRQ, we're going to do it the way we want to do it, aren't we? By the way, this right here counts as work, and you don't have to label all your binomial stuff. If you don't write that, then guess what you have to do? Label the things going into your binomial CDF. Notice that every time I don't just write the numbers, I write n equals, p equals, x equals. That's showing work. This is also work you need to show. So to solve this, we would do 1 minus binomial what? CDF, n equals 20, p equals 0.2, and x equals 11.
She ain't doing this. I'll put it down.
What's the answer?
4.096 is negative 9th power.
Okay, so 4.096 times 10 to the what?
Negative 9.
Which is approximately what?
Really small. 0.
Is there any possibility that any of her, what's the probability you're going to pass this exam?
Pretty low.
Pretty low. 20 questions all guessing randomly. So I want you to take it to those people who say, I'm just going to color in bubbles on the ACT. How many questions on the math section of the ACT typically?
70 or 60.
Yeah, what do you think the probability is you're going to pass that section if you're just guessing? Really, really, really low, isn't it?
Yeah, the first numbers.
It's what?
Oh no, I did something.
Did you do something wrong?
Oh, I thought I did something wrong.
Oh, no.
I put
What did the rest of you get?
P is 0.2, right? And X is 11?
I put in as
Yeah.
12.
Hang on. What did you guys get back there? 0.0001. Okay.
I didn't get that.
Sorry.
Even though we're going to see one. And so I put 12 trials.
It's still pretty close to 0, isn't it?
Basically 0.
Yeah.
I just had a smaller.
Why does it freak out when I do 1 minus answer? So when I did the regular binomial CDF, I got like 0.999.
Yeah.
Yeah, but when I do 1 minus answer, I got 1.01728.
That's what I got.
E the negative.
That means it's 1 times 10 to the what?
Negative 4.
Negative 4? That is the same thing. It didn't freak out.
Yeah.
Look.
You're making my brain freak out.
1, 2, 3, 4.
I wish they would just say that. Just give me a number.
You know how you can fix that?
Uh,
Multiply it by 10 to the 4th. If it's times 10 to the negative 4th, multiply it by 10 to the 4th. What do you get?
1.01. Which ain't right.
No, okay, hold on.
I don't know.
Let me think about how you can fix that.
No, I think I might be able to just let me double triple check.
No, there's going to be a way you can take it out of
Binomial
engineering.
CDF trials, 20. Yeah.
20.2 and 11.
Yep.
1,
Thanks.
EE, negative 4.
I want to figure out what I'm doing.
Right. You're not.
Math.
Well, you're what?
I get that.
Yeah. And then you do 1 minus that. 1 minus an answer.
Minus second answer.
Enter. Okay. That is that. Let me predict that. Huh?
Because when I multiply this by 4, it gives me 1.
Oh, go up to, well, let me see something.
Yeah, because right now, it doesn't, it's just a waste of space if it puts all that 0 before. So it takes away the 0 from the decimal, so it's a more readable number than just 0.000, 1,000 zeros in a row, 1. Oh, 161.
There ought to be a way you can go from scientific to not scientific.
There's one in the mode. If you really want
Mm-hmm.
Where?
You'll have to look it up.
Never mind.
Okay, so
Just know it's
do we have any questions at this point? Yes, no, we're good, we're not good? Here we go.
6, 7, 5.
6 and 5 are the same type, yeah. Just additional practice at it. So day 7.
All about polynomial. I'm so hungry.
Day 7
Me too, homie.
I know.
What's up? What do you have for lunch today?
Cottage cheese, I think.
Just
Blueberries.
cottage cheese. Get a spoon.
Cottage cheese and blueberries and I don't know, some other stuff.
Are you still lifting the tires and stuff?
I haven't been because of my knee. I finally literally just last week passed my 1 year mark of you're good and, what do I have this? You're good and now you can do whatever you want pretty much. Mark. But I was not okay before that. I got day 5, I've got day 6. Where is my day 7? I thought I pulled it today. This is day 7 homework.
I guess class is canceled.
Where is my day 7? Now I can still do the notes without it. Trust me on that one. It just doesn't give you the answers. It doesn't have the answers.
You're like a different key.
Okay, you're killing me. Go to whistling.
Oh, just you.
Oh.
Do you actually like things on Instagram?
Huh?
Yeah.
Got it.
I've had Instagram for I don't know how long, but I don't think I've liked anything.
This won't take long. All right. So here we go. I was recording all that, by the way. So that Riley and they won't feel like they're missing class. They can hear all the fun stuff. They hear you guys too.
Well, hey, Riley.
Yes, everybody say hi to Danielle and Riley and Colby. Yeah, poor guys and gals. All right, here we go. Let's finish up between now and after lunch. Finding the mean and standard deviation of a binomial distribution. So we're still doing binomial distributions. Next time we'll do geometric. You know what the only difference is between binomial and geometric?
Geometric is more than 2.
Geometric means you just pull until there's no set number of trials.
So it's not bins.
It's not bins. It fails the N in bins.
This.
Yeah, really. All right, so here we go. Mean and standard deviation of a binomial distribution. I want you to look at something. How do we find the mean? The mean right here, which is expected value, has a formula. This is on your stats formula sheet. It is N times P. What does that mean? What is the N? The number of trials. So this is the number of trials. And P is what?
Probability of success?
Yes. Probability of success. Now here's the thing. This is a shortcut because remember, we can create a probability distribution, can't we? How do we find the expected value of a probability distribution? Multiply straight down, right? And add them. So instead of having to multiply straight down and add them, we've got this shortcut. Boy, that's a nice shortcut, isn't it? We just take N times the probability of success. The number of trials times the probability of success. That gives us our average probability of success for that particular thing, okay? So let's look at this. It says, think about why this formula. Flip a coin 10 times. Guys, what's the probability of getting heads or tails every time you flip a coin? 50%, right? Well, if you have a 50-50 shot 10 times, and you flip a coin 10 times, how many of them should
50.
be
5.
5? Common sense. So let's take the number of times we're flipping that coin, which is 10 trials, times the probability of getting heads, and guess what you get?
5.
It works.
Excitement.
So, if your probability isn't 50-50, it's 60-40. If you were to flip a coin 10 times and your probability of success getting ahead is 60%, you'd expect to get 6. 10 times 0.6 is 6. So you see it works out beautifully, doesn't it? All right, so that formula works. This is an important one. Now look at the standard deviation formula. It is the square root of n times p times what?
1 minus p.
So it is the number of trials. This is success. This is what? Failure. Probability of failure. And this is your number of trials. And then we take the square root. That is also a formula you need to know. Which means the variance is just going to be n times p times 1 minus p, isn't? Because remember, variance is just standard deviation squared, right? So let's bring all of our vocabulary along with us. So here we go. It says, calculate the mean and standard deviation for the number of questions in Miss Bates's class. They would guess correctly on 20-item multiple choice quiz. So if we want to know the mean for x, how many trials, how many questions? 20. And what was the probability of them guessing for each question guessing correctly? 50%, not 50%? 1/5, right?
Was it 1/5?
Which is 20%, right? So what's the average number of items you're going to guess correctly on that 20-item multiple choice test? 4.
4. I hit.
That is not passing by any means, is it?
I said 40%.
So your average grade is going to be 4 out of 20, which is a 20% on the test, isn't it? Yeah, it sucks, doesn't it? All right, so let's find the standard deviation now.
Okay.
Standard deviation of x.
Square root 4.
20.
You don't just do that.
Did you do that?
No.
You just found the
No.
two. Is it M does-
Oh, yeah, you could
just
do
put in
4.
4 and then the 1 minus p.
Huh?
That was from the last.
5 items, or A through E, right?
The randomly generated.
A, B, C, D, E. It's from the previous question. Remember, it says Mrs. Bates' class would guess correctly on the thing. Mrs. Bates, there were 5 answer choices, so your chance probability if you guess correct is 1 out of 5. All right. So 20 times 0.2 times what?
0.8.
0.8.
And then square root.
That's failure, isn't it?
Square root of 3.2. 1.79. 9. That's
Yeah.
what you got.
It's about 1.789, 1.9, 1.79. Yeah. All right. So 4 with a standard deviation of less than 2 questions.
So some people made 60.
So let's ask ourselves what that's going to look like. You got 4 here, and then less than 6, and then 8, and then 10 would be 3 standard deviations out. So what's the probability of guessing more than 10 correct?
Very little.
Really, really, really small. I should be holding my hand out here for y'all, shouldn't I? Really, really small. So if we consider a normal curve for this, normal standard deviation curve for this, it's going to be really tight around 4, isn't it? Because that standard deviation is not very big. We're never going to get really above 10. If you guess more than 12 correct, or more than really 4, 6, 8, more than 10 correct, it's going to be a miracle, right? Very, very small probability. We'll start looking at you as a potential to be on the psychic network. All right? So, not going to be very good, is it? Histograms. What do we notice? When P is 0.5, 50-50, what is this going to look like?
Fairly symmetric.
What do we mean by completely symmetric?
Ours would be like this.
It means it's going to be nice and normal. Yes. When p is less than 0.5, in other words, if n is really small, fairly small, and p is less than 0.5, in other words, the success is not very high, it's going to be skewed what? To the right. Going to be skewed to the right, which means it's going to look like this more, isn't it? Think about what we just found with that 20% question. Didn't we find this was 4, 6, 8, 10, and this would be 2 and 0? We wouldn't even get 3 standard deviations over there, would we? So it is skewed to the right. The lower p is, the more skewed it gets. Yeah, but, you know.
And my teacher wasn't gonna be there anyway Friday, because she's gonna be in Nashville seeing Lion King.
Then-
and we're doing a packet, so I can sleep
Yes.
until I wake up.
So my guess is you won't have a Google Meet in that class.
Unless she's like mid show.
It's the same schedule as we had last year. Which is, God, I don't even remember.
Was it like 8:30 to?
I don't know, it's 45 minutes at a time. Hopefully they're gonna send it out to us. Let me,
Oh, is it like the 45 minutes and 10-minute break or whatever?
it's what the other, it was what it always has been. I don't even remember. I don't even remember what the schedule was. You'd think they would
I
send
think
it
it was
to
like
us.
8:30, 9:20, and then 9:30, 10:20, it was like that.
Yeah.
Oh,
Oh, ah!
Did you get that schoolcast?
Yep.
This is what we-
Yeah, we're not coming so long.
The candy starts once we go virtual.
so
I don't know about you, but
Don't put the mic.
I'm gonna go get my paperwork.
I have
Mine.
9. You just get it checked.
Just for tomorrow.
Huh?
I'm gonna go get my work for this mine for tomorrow.
Why not?
On paper.
Not yet, you're not.
No, yeah, I'll do it tomorrow.
Yeah. Oh, let me see if I can find.
Oh, I just forgot. AP environmental is gonna be so hard on mine. This is gonna be the worst.
Yep, it's gonna suck.
Yeah. We're gonna get test point boosts. Are we gonna do tests?
Yeah.
How so?
Well, if it's just for a week, no.
You'll push off the test?
I'll push the test
The
off.
test would have been next week though, right? Next Thursday?
Until, yeah. I'll push it off until after we're back from virtual. I hate having to do those kind of tests like that. It sucks. So we'll just cruise on ahead and start the next unit. When is the virtual schedule? Where did I find that?
Can we start at 8?
Hang on.
Let's just push it back to 9. Let's just push back class till 9. We get out at 12:30.
Yeah, we're going virtual starting tomorrow, and you can't be here tomorrow, so whatever you're gonna post, you better do before you leave for tomorrow.
We cannot be here?
No, they're gonna disinfect tomorrow. Just tomorrow, they're gonna disinfect the entire building. And then if you wanna come in next week and work from here. Now, we're on a virtual schedule, which Yvette Evans so lovingly said, you know the one. But they haven't actually said to us, because, those of you who were not here last year, obviously you know what it is. I'm trying to find it now, because I don't even remember what it was. So, I will.
Whenever we decide this.
AHS virtual instruction. Hang on, I might actually, no. It's not it.
So it's only tomorrow?
No.
They said they're gonna see about next
We are
week.
going virtual through the end of next week.
Some people are saying like that they were gonna play it by
No.
ear or whatever.
No. We are not playing it by ear. Here it is. Virtual schedule. First block is from 8:30 to 9:20. Second block is from 9:30 to 10:20. Third block is from 10:30 to 11:20. Fourth block is from 11:30 to 12:30, and then office hours for teachers are from 1:30 to 3:30, with no office hours on Friday. Okay, so this is virtual schedule. This is the virtual schedule we used last year, isn't it?
Sounds right.
All right. I'm going to print this, and I'm also going to share it with Kirby. Mr. Kirby. Coach Kirby is, or this is for Steve. Stephen Kirby. Eva. Carolboro. All right. So let's finish up here, please, so we can be through notes, and then we can move on from there. God almighty. This makes me nuts. Oh, ha! You know what? I bet I didn't turn this off. Nope, I didn't. Shoot. Oh, that's bad. We've been recording. And recording and recording and recording. All right, that's okay. I guess we'll go from here. All right, so it says when it's going to be skewed to the right. We know it's skewed to the right, don't we? Because remember this part right here, if we looked at what we did that previous example, it only went to 0 for little more than 0 for 2 standard deviations, didn't it? And what it says is the more, as p gets smaller, think about it, as p gets smaller, then it's going to be skewed even more and more and more to the right. Does that make sense to you? So it's going to go from this. Guys, you don't have to write this down, but I want you to see it. We're going to go from a 0.5 to this. This is 0.5. 0.5 is p. And then if it was at 0.4, then it might look a little bit more, little bit skewed. So this would be p is 0.4. And then 0.3 would be a little bit more skewed.
0.5 is symmetric.
Yeah, well,
Is the gist.
yeah.
And as it gets closer to 0, it's to the
Or 0.3, yeah. And it's going to get more and more skewed to the right. Okay? Now, what happens if p is getting bigger and bigger and bigger?
to the left.
It's going to go the other direction. Skewed left. The closer p gets to 1, the closer it gets, the more it's skewed to the left it gets, correct?
Yes.
So does everybody understand how this is working? All right. So let's finish up. It says, well, hold on. He said, we expect the biggest bar to be closest to the value. Yeah, no kidding. All right, so normal approximation for a binomial distribution. So if we're looking at normal approximations for a binomial distribution, we are looking at what? When can we normally approximate? As the number of fixed trials n gets larger. This is the big clue here. We have to have enough trials. Okay? As n gets larger, the histogram looks more and more like a normal distribution. So as n gets bigger, this thing becomes sort of normal. And it's most accurate when p is closest to what? 0.5. And n is relatively large. So now what is the rule for n? Well, the rule for normal approximation is a combination of n and p. This is what we call our normal large counts condition right here. You'll hear me refer to it over the next 5 or 6 sections that we do in this class is the large counts condition. Large count condition says if we take np and it's greater than or equal to 10, and, notice it says and, not or, and, n times 1 minus p is greater than or equal to 10, then we can consider this to be normal. Okay? And if it's normal, then we can treat it as a regular normal distribution. Normal CDF, normal PDF, all that kind of stuff, all right? So we don't have to worry about it being binomial. We couldn't do that with our one question, could we? No. We could not do that with a p of 0.2 and only 20 questions. Notice it doesn't say n is 20. The number of trials is big. The number of trials, if we've got a really low probability of success, then we're going to have a really big number of trials, aren't we? For it to become anywhere close to normal. Okay? Because we've got n times p is that combination. All right? So, 10% condition. There's another piece of this. 10% condition says this. When we're taking a simple random sample of a size n from a population of size big N, all right? So we're taking a scoop out of a big bowl. Think of it that way. We're taking a scoop out of a bowl. If the scoop is at least 10% of the bowl, this is what we call the 10% condition. All right, what does that mean? It means that we can use a binomial distribution. So we've got to be dipping at least 10%. The number of trials has to be at least 10% of the total population of trials. Okay? So this is the 10% condition says this. Or you can write it this way. In all honesty, I almost always look at it this way. N has to be less than or equal to 10% of the population. Now here's why. Why does it have to be less than 10%? I want you to think about what we said about independence. When we talk about independent, to use binomial, it has to be independent, doesn't it? My trial doesn't affect your trial. If we scoop too much out of the bowl, it's going to start affecting it, isn't it? The next one, and the next one, and the next one, and the next one. Think about it this way. If you've got a pool that you're trying to get a date out of, a pool of girls or guys that you're trying to date, if you date too many of them, that's going to begin to affect your results on the rest of them, isn't it? Make sense? Okay, so we've got to keep it down. We've got to keep it small compared to the overall population. That's what keeps us independent. And that's how you tell the difference between this and the large counts condition. This has to do with the size of your sample, right? For binomial. This has to do with independence. And you might make yourself a okay? We need to know that our samples are going to be independent of each other. If it's less than 10%, we can usually assume they are. Okay? Yeah. And you can look at that with cards, pulling cards. Let's say we have a deck of cards. There's 52 cards in the deck, isn't there? If I pull one card out and then I pull a second card out, is the probability of pulling the second card, is that going to change much from the first card? 1 out of 52, then 1 out of 51. That's pretty normal, isn't it? But when I start pulling, let's say 10% of 52 cards is 5 cards. Once I pull 6 cards out, now the probability is a lot different than 1 out of 52 is no longer 1 out of 52. It's now 1 out of what? 40 something, 49, 48, 47. That decimal number starts being very different, doesn't it? So you can see that it does start to make a difference when you pull too many out, when your independence suffers. All right, so, and notice what it says here. Violates the independence condition of the binomial setting. It says the actual probability of success on each trial would change considerably to affect our results. All right, guys. One more thing, though, is how do we tell the difference between these two? So 10% condition is what? Independence. But the large counts conditions is what? So just to reiterate, large counts condition proves normalcy, and the 10% proves, and if it's normal and it's independent, then we can do all kinds of stuff with it. And what you're going to find as we get further and further and further in is you'll be checking for this 10% and this normal condition a lot, okay? Using the large counts and the 10% condition. 10% is for independence. Large counts is normal. You need to get that committed to memory, okay? And I don't know how to tell you other than 10% sounds like independent. A little bit, doesn't it? But large counts doesn't. So large counts is normal. All right, so does anybody have any questions on anything we've covered? So next week on Tuesday, you will be virtual, won't you? Okay, so next time, I will put up